Okay. I've been waiting for this discussion for a while, Pete. It's great to have you here, and it's great to be talking about quantum. The linkages between semiconductors, state-of-the-art semiconductors, and quantum science are fascinating, and we'll get to that shortly. But I should just say that 21st century technologies really come down to 12 core technologies. And the foundational technology, really what's at ground zero, are semiconductors. And that we have the semiconductor AI nexus driving this feedback loop, which is now, of course, affecting everything from advanced materials to advanced manufacturing, biotech, every aspect of AI, hypersonic sciences, all of that sort of thing. And we were talking offline, and I think we agreed that the science of state-of-the-art semiconductors is really, for the human species, a zenith in technological accomplishments. I mean, to think that all the people in the audience, if you look at the chip on their phone, we're talking about billions, even up to hundreds of billions of little transistors the size of a human genome, stacked and actually performing functions on an atomic scale in terms of measurement. And one would think, to accomplish that, just to get one prototype to function is a massive accomplishment. But when you think about it, to mass produce with virtually no error, up to a trillion, right? So in 2023, we produced almost 1 trillion microchips, and they're, of course, ubiquitous. They're in everything. So naturally, as, of course, the audience is aware, this is at the heart of great power competition. This is at the heart of techno-nationalism. And so all of the dynamics of techno-nationalism, the weaponization of supply chains, innovation mercantilism, tech diplomacy, all of this is at play. So as we approach, and we'll talk about this a little bit later, Moore's law, right? As we approach sort of the end of the line, if you will, when microchips can't get any smaller, this is where quantum comes in, right? And so we'll get to that. I should actually start, and I think that's a good jumping off point. I mean, defining quantum is actually a pretty technical, pretty difficult thing, I think, for a layperson, somebody who doesn't do that for a living. How would you explain, how would you give a snapshot of sort of what quantum is and its relationship with semiconductors?
Yeah, so let me cover the full introduction to quantum computing and then a perspective on the history and significance of the semiconductor industry. That's a great question, Alex. Quantum computing is an idea that's decades old. Billions of dollars have already been spent towards this idea by governments and national labs and universities and so on. The basic idea is that if we can build a machine that manipulates information using quantum physics instead of classical physics, then we have new operations that we can do with information, and that gives us new algorithms, new strategies that in some cases are dramatically more powerful than the classical algorithms that we use today. We know of problems at the root of some of our biggest industries that can only be solved in this way. So I'm a technical person. If I look at the Fortune 100, sometimes to me that looks like a bunch of guys in suits shaking hands with each other. But of course, if we think about car companies, materials companies, energy companies, pharmaceutical companies, semiconductor companies, at the root of these giant industries is chemistry, physics, and math. And there are calculations that we would like to do regarding the design of drugs, the design of materials, catalysts, fertilizers, etc. Where as far as we know, a quantum computer is the only machine that can ever answer those questions. So this is why quantum computing has had this huge gravitational pull of capital, of talent, and a huge global effort to try to realize these machines. Nobody today has a useful quantum computer. There are very impressive demonstrators in many labs around the world, but nobody has yet reached the scale that is relevant. That scale is debated, But our view at PsiQuantum is that you need about 1 million qubits to do anything that's commercially useful. And 1 million sounds like a big number to a physicist, right? I started out in a research lab with handfuls of working devices. And 1 million is like a really daunting number. I used to float single atoms around in ultra-high vacuum and try to shoot them with lasers. Our CEO, Jeremy, who started here in Australia 25 years ago, used to take single phosphorus atoms with a little spike and try to embed them into a silicon lattice. If you're doing that kind of basic physics research, 1 million qubits sounds like a crazy big number. But as you point out, over the last 50 years, humanity has spent $1 trillion to realize the miracle, which is that you can build chips with billions of transistors, the size of a postage stamp. Each of those transistors is going to do 1 billion things per second without fail for years. And you give these things to your kids and you say, hey, please don't drop it down the back of the sofa. You know, it's like a crazy world that we live in. And so, yeah, we try to build our quantum computer using that semiconductor manufacturing capability. And that's part of the reason that we're optimistic that we can build it quickly.
So there are really 3 types of quantum science, right? There's the computing that you mentioned.
Yep.
There's sensing.
Yeah.
And then there's communications, right? And so PsiQuantum is focused mostly on computing or primarily on computing?
100% on computing.
Okay.
Yeah.
So in yesterday's opening talk, Dr. Eric Schmidt, he was a little bit lukewarm on quantum.
Yeah.
And so again, you and I have had this discussion. There are some challenges, right? So there's the cryogenic atmosphere, right? Mm-hmm. So the computer per se has to be in a very, very, very cold, sealed environment, number one. Number two, is it still prone to a lot of errors? I mean, must there be a lot of other technology to correct the errors that the quantum computer is making? And then I guess the third question would be, and I think you alluded to this earlier, practical quantum, right? When we go beyond solving big, prime factoring numbers for encryption and that type of thing, when can we expect to see quantum computing being applied for, biotech and on the military battlefield and that sort of thing?
Yeah, that's a really good question. So as far as errors, indeed, the reason that all of the systems that exist today are not useful is that they have too many errors. The errors build up very quickly in these machines. Google has one, IBM has one, many other companies have these kind of demonstration systems, but they're basically plagued by error. The only way to overcome that is with active error correction, and that's how you end up needing millions of qubits. And then, I listened to Dr. Schmidt's comments yesterday. I think his concern is around a killer app for quantum computing, as far as I understand. And it's definitely the case that the applications of quantum computing have been it's been a bit of a messy communication on those applications. The way I would look at that is if you went back to the very early days of conventional computing, if you went back to the very first conventional computers that were built, Alan Turing and John von Neumann and these early pioneers, and you ask these guys, what are you going to do with this expensive vacuum tube or mechanical computer that you're building? They'd say, well, we're going to do code breaking because there's a war on. We're going to read Hitler's messages. We're going to design nuclear weapons with these things. And we're going to do maybe some ballistics calculations. That's basically the motivation to build these early conventional computers.
Absolutely.
And you'd say, okay, have you got anything else? And they'd say, well, yeah, we're going to do code breaking, and we're going to do designing nuclear weapons, and we're going to do ballistics calculations. Or maybe one day we'll be able to simulate the entire human brain and, whatever. But yeah, it's basically these three. And it would have been fatiguing, right? Like just to hear this short list over and over again. Quantum computing has exactly the same situation, where if you talk to a quantum computing person and you say, what are you going to do? They'll say drug discovery, materials science, catalysts, fertilizers. Drug discovery, materials science, catalysts, fertilizers, code breaking. And that list just comes over and over again.
Yeah.
And it becomes a bit boring to hear that. But of course, any individual one of those items, if we do that for real, that is a profound impact. There are 1 billion people alive today who would not be alive were it not for the Haber-Bosch process, which we use to make nitrogen fertilizer. That's a single piece of chemistry where there's a pretty strong argument that it's responsible for 1 billion lives.
Yeah.
And so if we can use quantum computers to improve our design of drugs, design of materials, I think that's a very profound impact. The other reason that there is still some kind of concern over the applications of quantum computing is that the known algorithms historically have been too inefficient. And so when you compile them for the hardware, it's too expensive. And this is actually in very strong analogy with what happened in AI. And I think a lot of people actually don't know this history, where people knew decades ago that neural networks were a good idea. AI was established as a good idea a very long time ago. It took decades of sustained mathematical work to make those algorithms efficient and practical on realistic hardware. So ideas like transformers and attention, which you can read about on LinkedIn every day now, those ideas were essential for these algorithms to be actually practical on realistic hardware.
Yeah.
There was also, of course, a convergence with, and a very sort of serendipitous convergence with things that were happening in the semiconductor industry. A video games company was making chips that magically turned out to be the right chips to run these algorithms. Yeah. And I think we have exactly the same thing going on in quantum computing, where it has taken decades of sustained mathematical work to find the free lunches in these algorithms and to make them efficient enough to run on real hardware.
Yeah.
That's where we spend a lot of our energy. And then also, we needed to actually wait for the semiconductor industry to have the devices and the manufacturing processes that meet our spec for a fault-tolerant quantum computer.
And I think existentially, we have geopolitical impetus really pushing. It's an innovation race, right?
Yeah.
And I think that segues nicely into my next question, which is essentially public-private partnerships, right? So for a company like PsiQuantum, there are huge barriers to entry, obviously, when we're talking about quantum, as with semiconductors. And so there's a lot of money that's involved there, right? So funding has to come from public sources. Governments are now willing to put a lot more money in quantum because of the geopolitical component. What do you think needs to happen with public-private partnerships? Or maybe talk a little bit about what is happening with public-private partnerships with your company. But what do you think needs to happen sort of writ large to really push that innovation envelope in the quantum space?
Yeah, so there is, there's an unfortunate aspect of quantum computing, which is that small quantum computers are not useful. So if we want to access these kind of transformative, very exciting applications of quantum computers, there is a minimum scale which we need to exceed, and it's a pretty high bar. And so what that means is that, for us as a startup company, we have spent our resources, bunch of venture capital. We've spent that on, for instance, a manufacturing process that can make millions of devices. We do that in upstate New York in the United States at Global Foundries, which is a tier 1 semiconductor foundry in the same category as TSMC, Intel, Samsung, etc. And you can imagine that for us to stand up a new 300 millimeter semiconductor manufacturing process at Global Foundries, that is a very expensive prospect. We've put multiple multi-million-dollar pickup truck-sized semiconductor manufacturing tools onto the shop floor of a commercial semiconductor foundry. We've put superconductors into that fab, and we now make thousands of wafers in that factory. That's one of many large engineering projects that PsiQuantum has undertaken to enable the technology that we need. And so, our vision of a quantum computer is a 1 million square foot site in Brisbane that we announced very recently with a building scale machine on that site. And so, it's definitely interesting that is getting done, in our case, by a Silicon Valley startup company. that's venture funded. Now, we're very fortunate to have a lot of government support, especially here in Australia, but also from the United States. But yeah, it is definitely historically notable that a project that grand and with such strategic significance is being done by a private company, first and foremost. There are definitely historical precedents where you would say that is for sure something that a government is going to do as opposed to a startup,
Yeah. How significant is the security element, the alliance? Let's talk AUKUS, for example.
Yeah.
Pillar 2, technology transfer under that. Would all of this be happening without an AUKUS, do you think?
Yeah, I think AUKUS, of course, is very exciting. I'm British. My co-founders are Australian. They're also British citizens. We founded the company in the United States for the first 8 years of our life. And of course, so certainly what I can comment on is that Australia has been extremely forward-thinking in pursuing quantum computing in the universities initially. It's one of the very few places where you could actually do a PhD in quantum computing 25 years ago. The UK also is in that category, and the US also is in that category. And so I think there's a very, very natural alliance between those nations on this activity. Quantum computing also, of course, is a dual-use technology. Code breaking is not a civilian activity, I hope. The thing that I'll say about that is that if you think about technologies like GPS, the laser, radar, strong encryption, the internet, these are all technologies that came out of the military-industrial complex. These were all dual-use technologies. They were all export-controlled and protected and debated and so on. But of course, you have GPS in your phone. You use strong encryption every day. You might have radar in your car. You have a laser in your house, in your CD player if you've still got one. These technologies all ended up getting out into a commercially, overwhelmingly commercial context.
Yeah.
And we see quantum computing with having very much the same dynamics. There are absolutely sensitive applications of quantum computing which really need governments to be engaged and to be cautious about those applications. But we see it fundamentally as a commercial technology in the long run. And we're not really too worried about the sort of long-term trajectory in that sense, yeah.
How do we avoid another TSMC in the quantum field? In other words, with such high critical mass and concentration, specialization, how do we sort of have more players, have more diversity, have supply chain security, resilience?
Yeah, so I'm really happy that we're sitting on this stage talking about this. I think I thought it was an extraordinary moment when President Biden stood up with a 300 millimeter wafer in his hands. Like for a president of the United States to hold a silicon wafer, a lot of people have never seen a silicon wafer in their life. A lot of people who work in technology, I've found out, don't know that wafers are round. It's like it has been an amazing situation. But of course, as of recently, there is clear awareness of this strange situation where human beings are increasingly developing critical technologies, foundational technologies, where the physics and the engineering of that technology is so hard and so demanding that there is a physically motivated concentration of power. So semiconductor manufacturing, AI supercomputers, quantum computing, maybe one or two others. These are technologies where, as far as we know, barring some miracle, they are going to be extremely hard, extremely expensive, extremely demanding facilities that have to be built on some piece of land. And with semiconductor manufacturing, we have seen this like insane concentration of power into relatively tiny areas of land. And certainly, when we announced our plans to build our first generation system here in Australia, this was like front of mind for us. It was a very exciting aspect of that announcement. Because, yeah, I think if you wrote a science fiction novel about quantum computing and geopolitics, like the lazy default story would be that there is a giant quantum computer in the United States and there is a giant quantum computer in China, and that's it. And that's a bit of a boring story, if you ask me. So I think, you know, it's really wonderful, actually, that we are hopefully in a position to mitigate that kind of situation that we have had with semiconductors. I live in Silicon Valley. Of course, nobody makes chips in Silicon Valley really anymore.
Right.
It's a pretty sad situation. And yeah, hopefully we can mitigate that to some extent in quantum computing. But there also needs to be a recognition that you cannot have, like, in the same way that you cannot have thousands of tier one semiconductor foundries, like physics and reality is not going to let us do that. You also, as far as we understand, cannot have thousands of utility scale quantum computers and build one in your backyard. It's not going to happen as far as we're concerned.
Okay, Pete, one last question before I open it up for Q&A from the audience, and that is, let's come back to this dual use dilemma, right? So there's obviously a very dark dystopic side to the use of quantum. You know, yesterday we talked about AI and generative AI and you know, where that might be going. How do we maintain that really critical balance between positive development and preventing, you know, bad actors from really perverting the uses of quantum?
Yeah, so I think there are two sort of it's a good question. I think there are kind of two natural reasons to be optimistic here. The first is that I'm very lucky that I don't have to sit on the stage and debate the chance of my technology killing all humans, which we had. That was the debate that we had yesterday. I'm happy that that's not really on the cards. And then the second thing to say is, look, quantum computing is a general purpose technology, just like computers, just like books, just like many other things that human beings have come up with that can be used in ways that are uncomfortable and also used in ways that are profoundly positive for human beings. And you know, there's really one application of a quantum computer that is, you know, worth worrying about, which is code breaking. You know, breaking all encryption, basically. That is definitely something that governments need to pay attention to. There's an intrinsic piece of good news there, which is that actually, in order to do code breaking, we would need much larger quantum computers than the first commercial machines that we plan to build. And so we do expect that you will be able to solve commercially relevant problems in chemistry and in material science and physics type problems significantly before we have machines that are big enough to break cryptographic codes. And of course, there is also an ongoing effort to try to make our conventional cryptography resistant to the existence of a large quantum computer. This is a post-quantum cryptography effort, which has been going on for some time now. So I think there are good reasons to be optimistic that that will be a controlled technology, and that we have mitigations against the sort of disaster scenarios of those implications. But overall, I would say, again, this is a general purpose technology, and human beings, by and large, are trying to do the best for ourselves. And we don't want to use that technology to mess things up. We want to design new drugs, design new materials, usher in a future where we have mastery over chemistry and physics. Sounds like a wonderful future to me.
Excellent. So for you original Blade Runner fans, or the movie, there are no future Tyrell corporations using quantum?
The aesthetics is different. The aesthetics is a different question.
Okay. So more human than human, right? Replicants? Okay. Excellent. All right, so we have about 5 minutes left. Any questions from the audience for Pete? I see one straight back there, one up front here. Better put my glasses on. Sorry, guys.
Hi. Yeah. Oh, sorry. So I'm Rajiv Shah. I'm an ASPE fellow, and background in quantum physics. Actually, I was quite interested to hear what you said. One comment I had on the interesting thought. So, if you build the first quantum computer, that's like us having the first silicon chip or the first silicon wafer or something. We need an ecosystem around that to turn that into something useful. So I guess I'm interested in your thoughts about what needs to be done to build that ecosystem around the hardware manufacturing.
Yeah, around the hardware manufacturing, yeah, that's a really good question. And I'd say also that obviously extends to applications. Again, we're a startup company. We're very focused. We actually have very broad scope. We touch on everything from materials development to device design to layout, packaging, assembly. We build 2-meter high stainless steel cabinets where we cool our chips to liquid helium temperature. The list goes on. We have very broad scope. But this will be a grand project. It's a very large facility. It contains a lot of very advanced technology. And our view is that building a useful quantum computer is a species-level technical challenge. It's one of the hardest things that humans have ever tried to do. And we're not going to get it done without assistance from all sorts of different interested parties. Universities, national labs, startups, government, the full list, industry, contract manufacturing, semiconductors. We're really, really keen to collaborate as far as possible with people who want to help us get this machine built. And there are a very, very broad set of opportunities to do that, including applications work, working with potential end users of the machine, people who would maybe benefit from running algorithms on this system. Yeah, I think it's absolutely crucial that there is a healthy ecosystem around not only our activity, but quantum computing more generally in Australia, in the US, elsewhere. Yeah, it's a species level challenge.
Thank you.
And it sounds like that you've described an ecosystem like your new operation in Chicago, right, outside of Chicago. So all those parties, you mentioned DARPA in our offline discussion, and universities and everybody. So you've got that ecosystem going. I think we had another question right here up front, from the lady up front here.
Thank you both for that very interesting discussion. I think I'm just fascinated about quantum computing and semiconductors as well. My name is Jenny Wong Leong. I'm from ASPE, and we've been working on the critical technologies. Just going to wonder about a very kind of how would the landscape look like in terms of a quantum computer. It needs probably the liquid helium temperatures, but also probably quite sensitive to magnetic fields, for instance, right? So in terms of rolling it out, it's kind of not like the semiconductor chips that we have operating at room temperature. I'm just trying to understand and sort of imagine what the landscape look like. Would it be on the factory floor in Queensland? They'll be making one quantum computing at a time.
Yep.
But there'll probably be maintenance, for instance, into maintaining this kind of very sensitive conditions.
Yes.
I just want to understand. Thank you.
Yeah, so it's a good question. Quantum, our company hasn't really spent a lot of time publishing papers and talking to journalists for the last 8 years of our existence. Sometimes people think that we are a secretive company. Actually, we're just really busy. But we'd be very delighted. We're very, very happy to talk to anyone who wants to understand our technology. We recently published our first hardware paper where we actually shared some of these details. We've also shared a lot of architecture papers where we talk through how the machine will come together. But to answer the question, for us, what you should envisage is a building scale machine that looks like a supercomputer or a data center. Lots of racks in a building, in a warehouse. Those racks are networked together with standard telecom fiber. Each rack is cooled to liquid helium temperature. So we flow liquid helium into the back of these cabinets. They're actually built by a contract manufacturer who normally builds fridges for the food and beverage industry. So it's quite exciting to me that it's not an alien piece of technology. It's stainless steel fabrication, pipes, valves, vacuum systems, stuff that would actually be very familiar to a petrochemical engineer or a wastewater engineer. But they're big stainless steel cabinets, and then we put lots of chips inside the cabinet. Those chips are built in the United States and will be shipped to Australia. And then they're packaged, assembled, fiber is attached. And there are very serious challenges to building and operating these machines. Running at liquid helium temperature is not something people do every day. But of course, that's where we've been spending our resources to this point, is to mature and establish our ability to build those systems, to make them reliable, to operate them. And it's a grand challenge to get that full machine together. But yeah, that's what we think. And then, of course, quantum computing is fun, partly because there are lots of people who disagree with us. You know, there are other companies who try to build things in different ways, Google and IonQ and IBM and many fantastic Australian quantum computing efforts. And in some cases, those guys are envisaging a machine that looks very different to that building scale facility. But yeah, our view is that it's a warehouse-like system. Yeah.
Okay, we have gone a couple of minutes over, but I guess we can take one last quick question if that's okay. Yeah, all right.
Thank you, Pete and Alex, for a really fascinating conversation. Vikram Sharma, Quintessence Labs. PsiQuantum, of course, is very much at the forefront of this capability development in quantum computing worldwide. And I think you just started to touch on it in the response to the last question. But I'd love to have your thoughts around what you're seeing worldwide in terms of the competitive landscape in quantum computing.
Yeah, so
Great
I think, so thanks, Vikram. So I've been in quantum computing for 15 years. My co-founder and CEO, Jeremy, has been in quantum computing for 25 years. Quantum computing is a pretty crazy space in that there are a lot of people who have spent their entire adult life trying to realize this machine. Like tens of thousands of our best scientists and engineers have already spent decades of their life trying to bring this machine to reality, which is a pretty crazy situation. The good news is that we think we're pretty close to actually doing it. But to the question on how the competitive landscape is evolving, Google, Microsoft, IBM, Amazon, Intel, I'm forgetting some, they all have big quantum computing efforts. There are quite a few very well-funded startups. There's actually something like a handful of public quantum computing companies today, but nobody has a useful machine.
Okay.
The main evolution is that people have gone from where they started, which is always university research. All of these efforts are started by university academics, almost without exception. And they start out in an academic mode of operation. Make some cool demonstration, get something working, publish a paper, make some press releases. That has kind of been the mode of operation in quantum computing for a long time. There was a lot of optimism for a while that small machines would be commercially useful, maybe 100 qubits. There were a lot of people that hoped that that would be a commercially valuable system. What you're seeing now, like the overarching trend in the space, is a grand kind of swing to the recognition that you're going to need error correction and that this means you're going to need big systems. 1 million plus qubits, full error correction, chip-to-chip connectivity, much higher cooling power. And if you look at what IBM has been talking about recently, Google's recent results that are very impressive, you're seeing a big swing towards how do we build the real system? Stop doing demos, stop publishing papers, and like how do we build the real thing? And I think that's a very, very healthy evolution for the space here in Australia and globally. Yeah.
Great. Well, Pete, thank you very much. Fascinating discussion.
Thank you. Really
I hope we
appreciate
can continue it.
Thanks,
Thank you.
Alex. Thanks.